Okay, today let's start the chapter 6, conservation of momentum. Okay, this is the important chapter, and usually, historical speaking, students have a difficulty solving problem for conservation of momentum. Okay, so let's look at the conservation momentum equation first. Remember, momentum F equal to ma, right? That's Newton's second law. So in a particle, a Lagrangian system, solid mechanics. Okay, so summation of F equals to ma, right? The combination of the overall force equals m times mass times acceleration. So m mass usually is constant, so d mv over dt, dv dt is acceleration. Okay, so that we can say it's the momentum of the entire system, d momentum of the entire system over dt, that equals f, summation of f. Just like I show you in the class example in the early chapters, if your moving vehicle suddenly stopped, like hit a wall, hit a object, then the vehicle will be damaged because of the force it created by the changing speed, right, from a certain speed to zero. So the changing of the speed ma will result in a force. Okay, so that's the conservation of momentum in solid mechanics for a particle. Okay, so now we'll look at in fluid mechanics. Okay, it look a little different. So initially the equation is also still the same. The summation of force equals to momentum of the system over dt. The momentum of system over dt equals the mass velocity over dt. Okay, but remember, our velocity is not like in the velocity in the solid mechanics. It's not just vt. It's the velocity, the function of x, y, z, and t, right? So if you take derivative respect to t, it will be different. So that's the theory of d momentum over dt, which is equal to d over dt integration of velocity density integrate over the entire control volume plus the flux through the control surface, right? The velocity times rho v dA. Okay, remember, similar to the conservation mass equation, right? Rho v dA integration, that's the mass flow rate, right? That's the mass flow rate carry the velocity going through the control volume. That's the momentum flux through the control, carry through the control surfaces. Okay, it's a flux of momentum through the control surfaces, the second term. So that's the general equation now for the conservation of momentum in in fluid mechanics. So if you want to explain it in the real physics, read the real world, what does that mean, the equation? Okay, you see the first term, it shows the total momentum change in a system in terms of time, right? Time rate of change. Then equals to overall force, right? And also it's that change of momentum in the system equals the change of momentum in a control volume in terms of time, right? See the integration over the control volume, or d over dt. So that's the change of momentum in the control volume. That's the transient unsteady state term, right? d over dt. Plus the momentum going in and out the control volume through control surfaces. Okay, so that's the equation, right? That's the meaning of the equation. So similar to conservation of mass, we ask a couple questions. Is the flow uniform, right? That integration, surface integration, mass flow rate, rho v dA. If it's uniform velocity, then you don't have to do that integration, right? So if it's uniform inlet and outlet, the equation becomes this. of course, that integration, volume integration, we can say, hey, that's the total momentum in the control volume. So let's say d momentum in the control volume over dt plus the momentum out, which is m dot mass flow rate, which is the integration rho vda, right, on the control surface. Mass flow rate times the velocity. So the momentum out, m dot o vo, okay, the summation, if there's multiple inlet, multiple outlet. Then minus the summation of momentum in, m dot I, b dot I, through control surfaces. Okay, again, if it's uniform velocity, the problem is a little bit easier to solve. You don't need to solve that surface integration to calculate the mass flow rate, right? The velocity is constant. You can move the velocity out of the integration also. Then it becomes mass flow rate m dot times the velocity. Okay. Then if it's a steady state, the second question, right? If it's a steady state, then this is d momentum in the control volume over dt, that term becomes zero. This is unsteady term. This is the time rate of change. If it's a steady state, it doesn't change with time, so this term is gone. Okay. So now you know if it's uniform velocity plus steady state, then summation of force will be just equals to the second term and the third term in this equation, right? Summation force equals to momentum out minus momentum in. So that's steady state, okay? If the uniform, it becomes simple. Now you know if you solve conservation momentum problem, you need to calculate the summation of force, right? Summation of force equals to the change of momentums. So summation of force, for solving a problem, you need to draw a free body diagram, definitely, 100%. Okay, if you draw correctly free body diagram, you should be able to calculate the summation of force at least. Okay, then you also, in the right hand side of the equation, you need to draw momentum diagram. Okay, momentum out, momentum in, right? So then summation of force will be equal to the change of momentum. So two diagrams then you need to draw for solving the problem. One is a free body diagram, okay? One is a momentum diagram. So let me show you one more time the example of free body diagram. So the force terms. Now you know your summation of force. This is dynamics, right? This is not statics anymore. If you draw a free body diagram, your summation of force is not equal to zero, right? It's different. It's not equal to zero. Then equal to the momentum change. So, but you still need to draw the correct free body diagram to include all the forces. Okay. So this is the example. I'll show you an example. Okay. Let's see. This is the pipe. You know, a pipe flow going to this circular shape of pipe. Okay. Flow from bottom to top. The diameter of the pipe is d. The height, the length of the pipe is h. The z direction is going up, right? Okay, so this is the free body diagram for these problems. So in this particular problem, how many forces? Okay, there are many forces in here. Okay, first of all, you have the weight, right? W always going down, sure, no problem. And you have pressure forces. Now you know in the flow you have pressure, right? So in the bottom surface you have the P1A1, that's your pressure. So, assume the pressure is constant around the cross section. Okay, so well, first of all, this is the control volume. You draw a free body diagram, you need to know the body, right? Obviously this problem, the body is the portion of the pipe, right? Okay, the bottom, okay, you have P1A1. And you also at the outlet, you also had pressures, P2. So the force is P2 and A2, right? In the other end. Okay. But notice the flow direction is going upward. But the P2A2, the direction of that force is going down. Okay, to the surface. Remember, all the pressure force are towards the surface. Okay, just like you're underwater, for example. Underwater, you feel pressure. Doesn't matter your orientation of your face. you always feel the pressure push into your face, right? So the pressure forces always go towards the surface. Okay, be careful. It doesn't matter the flow direction. Okay, very important. You need to know how to draw, then what's the direction of the pressure force, right? There's one more force in this problem is the shear force, right? You have a shear stress, the flow is going upward, so your shear force on the surface is going downward. The shear, try to stop the flow flowing from the flow direction, right? Okay, so after you draw the free body diagram, you should be able to write down the equation for summation force, because in here, in the conservation momentum equation, you need to know the summation force, right, in this country volume. So your summation force in this problem, obviously we need to follow the sign, follow the direction. Z is going up, is the positive Z direction. So summation force along Z direction equals P1A1 positive minus P2A2, okay, minus W also downward, right? Then minus the shear force. Okay, shear force is also downward in this problem. Okay, so A1 and A2 obviously is the same, so you can combine the first two terms, so become P1 minus P2 times the area, cross-sectional area, which is in this problem is quarter pi d squared, right? We know the diameter is d. Okay, gamma, how do you calculate W with the weight? In this class, you can have a simple equation, gamma times the volume for the weight, right? Okay, gamma times volume. So volume of this cylinder is the bottom cross-sectional area times the height, quarter pi d squared times h. Okay, this is the weight. Then the shear force is shear stress times the surface area. Be careful, this is the surface area, outer surface area of this pipe. So it's a shear stress times the surface area is pi d, the circumference of the circle times the height. Okay, so this is the summation of force in this problem. It doesn't necessarily mean it doesn't necessarily equal to zero. Okay, this is a dynamic problem. In statics, summation force should be equal to zero, but here in dynamics, that equals to the momentum change. Okay, so this is the example for free body diagram. I would like to emphasize the free body diagram one more time, because in this chapter, every problem you need to draw free body diagram and the momentum diagram, and then put the equation put the equal sign between the summation force and the summation of momentum to solve problem. Okay. Okay, we will have a lot of examples for these chapters. Okay, so let me give you the general 3D momentum equation for the Cartesian coordinate. Okay, so this is the equation you can use for the most of the problem. Okay, sometimes it can be simplified to 1D or 2D. Right, this is a 3D. So if it's a 3D, you have three equations, fx, fy, and fz, right? You have to decompose into the components, right? For both force and momentum are vectors, so that's the only way to solve a vector problem, to separate into fx, fy, and fz. Okay, so fx equals to d over dt, the momentum in the country volume, with the x direction velocity u, right? Then plus the momentum out minus momentum in. Both of them are in x direction. You see mass flow rate OX. Okay, that means mass flow rate outlet at the x direction. Okay, it's a component. UO means x direction velocity at the outlet. Okay, outlet velocity, U components. Same thing for the inlet. IX, inlet mass flow rate in the x component. UI is inlet velocity at x component. Same thing for the V. For y component momentum equation, Fy, then you use V instead of U for every term. Momentum MOY means, M.OY means the mass flow rate. along at the outlet, right? For the y component, okay? M dot I y means the y component, the mass flow rate inlet, okay? VO, VI, inlet, outlet and inlet velocity, y component velocities. Same thing for FZ, then it becomes W, right? Third component. Okay, so that's a general equation, depending on the problem. This is including the d over dt. It's unsteady equations, but most of the problem you will see in chapter 6, it will be steady state problems. Okay, so you don't need to worry about d over dt. Okay, but for the momentum in and momentum out through the control surfaces, it could be uniform and it could be non-uniform. This is the uniform equation, right? Uniform velocity. But if it's non-uniform velocity, you have to keep the integration, right? To integrate the momentums through the control surfaces. Okay, so we'll show you some example for unsteady state problem too. So you will see. Okay. So before I give you any examples, let me emphasize on the strategy for solving conservation momentum problems. Conservation momentum problem, some students will feel it's difficult. So we have to have some strategy, to guarantee we can solve the problems. So that's a process, okay? So you need to draw the free body diagram and the momentum diagram. So you have to identify the control volume. So sketch the control volume. Okay. So for the previous example, we showed the pipe. That portion of pipe is your control volume. So sketch the control volume. Then on the control volume, you can draw the free body diagram, right? You can draw the forces. Okay. So FBD is the free body diagram for the force. Then for the same control volume, you can draw a momentum diagram showing the momentum out and momentum in, right? What the direction, okay? Use arrow to represent it. Again, momentum is also a vector, so you can freely use those arrows, okay? So with this diagram, you put an equal sign between these two diagrams, then you can write down the governing equations. For the free body diagram, you can write down the expression for summation of force. For the momentum diagram, you can write the expression for the momentum out minus momentum in, okay? Then decide a steady state or unsteady, right? As I said, most of the problem you see it's steady state, so you don't have the d over dt terms, okay? Uniform or non-uniform inlet and outlet. If it's non-uniform, you have to use integration for the momentum through the control surface terms, okay? If it's uniform, we can just use the mass flow rate times velocity as a momentum, right? Then after you write down the equation, you can solve the equation to solve for some unknowns. Okay, so this is the process of solving conservation momentum problems. Very important.